we've had lots of great discussions and talks today, focused on a lot of the important things, the business, the people, the process, and they're really, really important to make things successful. You can't really have, you can't really use AI or, data analytics or whatever you're trying to use without really thinking about what's the problem that you're trying to solve. That said, I'm going to focus on a different part of that space, the AI space and some of the systems pieces, I guess. That's something I really enjoy and I'm really passionate about, and also have the pleasure of working with every single day. So it's kind of fun. So let's start with some of the things we've been doing, and this is going back a few years. We started this group focused on deep learning in 2011, so this is from 2012, and we really started to make progress. And one of the first things we tackled was speech. So speech, if you've use your phone today, you've probably used speech in some fashion. You probably say, "Okay, Google," or Alexa, or whatever else you use. And the first thing that's there is you want to recognize what the person's saying, and then of course do something with that. And so back in 2012, when we really used this new technology and we pushed the research on that, what we did was, it was a really large team, lots of researchers doing different kinds of things. What it changed was over the last 20, 30 years, whatever research people had done, the change in that 1 year of research was equivalent to the last 20 years of research. This is in the words of researchers in that field. And it really changed how people think about speech. Before that, speech was like, yeah, there are all these dictation things. People kind of use them. But after that, like in 2012, 2013, that's when people started using it every single day. Because yes, the UIs got better, but it's at the core technology that really made a difference. That's what got better. And so we, of course, have used it for a lot of our key products, and this is Google Home. Hopefully, many of you use that. We use that as a core part of it. That's the first thing you interact with. That is the interface that you use to interact with Google Homes. And one of the first things, so this came out something like 3 years ago, I guess. And one of the first things that excited me about this technology here was, before this, Echo was already out in the market, and in fact, I had one at home, and I was using it. I had a 2-year-old daughter. She was 2 at that time. She's 5 now. And she would try all kinds of things, and it almost never worked. She would say, "Alexa, something, something." And one day, I had a test thing at home, and she tried it with, "Okay, Google," and she was barely able to say stuff. And it actually recognized what she was saying. So I was like totally floored. Wow. So there's some technology that we're building that's actually making a difference because the technology is better. Yes, we are trying to solve the same problem, but often the core technology that you use and you improve, that does make a difference on what the outcomes you get as well. In other areas, of course, vision. This is something that's really important to us as humans. We use it in every single interaction we have with other humans, also with our applications and so on. And back in 2011, again, computers, there was this notion of computer vision. It's a very old field, but it was still really far behind what humans were. And the difference between that 5% and 26% is basically you can't use it for most things, right? It might be a first pass at something just to cut down some costs. Yes, you do that. But in terms of actual consumer-oriented things or things where you care about that accuracy, it's just not going to matter. But just fast forward a couple of years again, and in 2016, based on all the different kinds of research we've done and improved, that's now come down to 3% errors. So that's actually better than humans. Again, in a very narrow thing, computers are still not as good as us in identifying all the kinds of things that we can do and being as general as we are. But in very narrow use cases, when you have the kind of data sets that you can train these on, they can actually do way better than humans. And that really is a game changer in terms of what we can do with them. So let's take a look at some of the things we've done. And this is, again, thinking from what are users looking for? It's, how do they want to use this? We used to have, before Photos, we used to have another app. And the first thing in Picasa was you would get all these nice pictures that you've taken, and you can look at it by time, but anything else you had to label it them yourself. That was okay maybe back then because we didn't have smartphones yet. We weren't taking pictures all the time. But as we got smartphones, as we were taking so many pictures, that just wasn't going to scale up. And what this technology allowed us to do was to really label these pictures automatically. Now, I have all these pictures. I don't have to think about what they are. I want to look up a dog. there are all the dog pictures and so on, right? I want to look for my daughter's pictures. I can see them right there pretty easily. And that's how the technology really helps you change the kind of products that you're trying to build. Of course, we want to combine those. So you can ask it to just look for pictures of cats and really understands what you said, does a regular search for those pictures, and then shows that using combining those two. Of course, it's not just about consumer apps. We didn't touch too much upon healthcare today, but that's a really important field for all of us. There's lots of analytics that we're doing. Fractals has Cure.ai working on this area as well. And one of the areas is pathology. Turns out in healthcare there are lots of pictures as well. Whether it's X-rays, whether it's in this case pathological images. There are all kinds of pictures that you can make sense of. And really applying the same kind of technology in taking those pictures and seeing if we can do better than what we're doing. And turns out, yes, if you have enough training data, you can do a lot better. So trained pathologists on this kind of thing do a localization score of 0.73. This is just a metric people use to track how good we are. And these algorithms can do way better, right? And this is true for a lot of different areas in healthcare. So really, it can push the state of the art, push the boundaries of what we can do with things. One of the things about this is often people mix up things where, okay, so these are better than doctors, so don't we need any doctors anymore? That's never the case, right? We need tons and tons of doctors, and there are lots of places in the world that have no access to doctors. This has the potential to really change that and bring access to doctors in places that are not there. Bring access to it to people that really need this kind of support. One more area that we applied this to was the brain itself. We've learned, this whole field of deep learning has learned from the brain. And one of the things we want to do with that is to understand the brain better itself. So there's this field called connectomics, which basically tries to see exactly how the brain is wired. So in this case, this is the brain of a zebra finch. It's a little bird. And they take that brain, take a slice of that, slice it up very thinly, and look at really tiny cubes. Use that to really paint all these different things in color and identify, connect all these things to make a full wiring diagram. And what these researchers have done is come up with ways to put that together. And very recently, they were able to take the brain of this common housefly, as that's known, Drosophila melanogaster, and really map out the entire brain. So they've made it available to lots of people, researchers, to really use that to understand the brain. And turns out this is still way smaller than our human brains, of course. This is something like 10,000 neurons, I believe. Rats have something like 10 million, and we have something like 10 billion. So there's a long way to go. But we've mapped out the entire brain for this little tiny insect, and we can start to understand a lot more about the brain from this. The speech and vision are things that have been, we've been pushing on, and that's what people often think of deep learning as. But more recently, over the last year or two, we've seen huge improvements in language understanding as well. So last year, we published this new kind of model called BERT, which basically made huge strides in learning from all kinds of text corpuses that are around. And once it learned that, it could be applied to all kinds of text problems. So in this case, it was applied to this question answering data set where it's trying to really answer questions that people have asked. And as you can see, it actually does better than human performance in this case. Of course, again, this is a specific task. One thing you'll notice is across these different tasks, AI is still fairly narrow in that if you give it a very specific task, if you know the problem that you're trying to solve, AI can definitely help solve it for you. But you have to know what the problem that you're trying to solve. You have to be able to define it. So all the things that earlier Shrikant and Guy talked about, those are still very, very important to combine those with this. So with this language, of course, as Google, we're a search company, and that's still understanding language, understanding all the text around us is still very, very important to us. And we use that to improve the search that we do for you. That's not the only thing. We've used it to improve things like translate. And in this case, this translate model is running right there on the phone where it takes a picture or just, you point the phone at something, point it at text, It figures out what language it is, then converts it to the language that you're looking for, and shows it to you right there. So it's combining a whole bunch of technologies there. It's not about just taking the basic thing, but really thinking about what are users looking for and solving for that. This is really amazing in that it doesn't need to go to the cloud. It can run right there. In fact, I was there in China last year, and of course, I don't know the language. I don't know the script. This was my only way around in terms of just even simple tasks like reading the menus to figure out what I want to order. Of course, we use it in all kinds of devices. So in this case, we have some of the hardware devices we've launched recently. In every single device, we've integrated the core technologies in many different ways, and one of them being Google Home. Of course, we look at, the speech part, the recognition there. We're looking at, when we display images, you can show searches there and stuff as well. In everything, we're looking at using these technologies to improving the products. Comes back to you want to solve and you want to improve products to, what the users want. But here's a great technology that you can use to improve those. Shrikant mentioned this one a little while earlier, AlphaZero. So this, of course, this worked on or improved upon a lot of work that Google had done before in terms of playing against lots of games. So in this case, AlphaZero can actually play chess, it can play Go, and it can play Shogi, and all of them better than the best humans in the world. And it does that by focusing on some core algorithms and really uses these techniques, uses these games to improve the core algorithms themselves because they're more valuable than just beating humans at those games. Beating these players at these games is fun, and the players like it as well, that they can play against, they can be challenged more. But what's more important is, can we use this technology to really deliver and build something more? And so it turns out we can. One area that we are excited about is robotics. So AI is only as good as what you can do with it. In this case, you saw some examples of robotics a little while earlier where Shrikant was showing the robots on the factory floor in Tesla. Traditionally, what robotics has been about is, okay, you have this robotic arm or some kind of robot. You spend a lot of time programming that robot for exactly that one task that you want it for. And once you've done that, you put the robot to task to do that. Works great if that is exactly the task that you want to do. If you move things a little bit, for example, your assembly line is slightly shifted, it's probably not going to work. So what we saw here and what we are aiming to do here is this robot where it was just picking up these balls and throwing them or picking up different kinds of objects, it's learning to do that completely from scratch. It's told that that's its goal. Basically, it needs to pick up things and throw there and get them in that thing. And it's really learned that from scratch, but hit and try, just like kids would. And it's really leveraging the same sort of technology that we used in playing those games to improve this as well. It's, of course, not just that. It's a combination of many different technologies together, but it's really leveraging those technologies to make something that's actually going to be useful. For example, you could use this. You probably don't want to throw your cars around, of course, but you could use this in the factory floor for different kinds of things as well. Here's another example where we're trying to combine some of the different technologies of, in this case, figuring out where it needs to go. So some of the same things that we use in the Waze app is used for navigation here in this floor, where it knows it's told, okay, it needs to go from point A to point B. There, unlike Waze, it actually has no idea where the road is. It needs to figure it out based on everything it sees. It needs to figure out the obstacles, and those are changed all the time. So it's not really trained at all. It just needs to learn that from scratch. And it's really combining all these together. So these are some great things we've done with AI. So let's quickly take a look at what the core technology is. And many of you might, since you're in this field, you're probably familiar with some of this. The basic technology we use in there is called neural networks. You might also hear of it as deep learning. And the basic idea here is you have some input that you take it through a series of functions or layers, as we might call them, to get an output. Now, the way you look at this, the way you train it, is by giving it lots of examples. Here's a very simple case where you give it 5 photos which are labeled, so you're telling it exactly what the result you want, and then for each of them you give it the output. So what it's going to do is for each of those labels, it's going to try and make a guess, see if it's right. If it's right, great. If it's not, it's going to learn from that and improve a little bit to really make a small adjustment so it can make a better guess next time. And then once that's trained, then you can apply it to really give it a new image, something that's not seen again ever before. Doesn't have to be an image, of course, can be speech, text, database, whatever kind of stuff that you want to do, and use that to test it. And so in this case, it gets it right. So one question that often comes up is, this technology is very old. In fact, neural networks has been around since, 60 years or something. And so what's changed now? And how are we seeing this? And so, one of the things about, say, 20 years ago or so in the 80s and 90s was machine learning, and there were lots of other forms of AI as well, that are the scale that we had, the sizes of data that we had, and the kind of capabilities that we had from a compute perspective only allowed us to do so much. And with that, the kind of things where we were basically with what the red line shows. And where we've moved now is we have a lot more compute, and that's allowed us to move this needle towards the right, where leveraging more data, leveraging much bigger models where you can actually leverage these neural networks to do a lot more. Of course, as Kai was saying earlier, if you don't have that kind of data set, this is not the only thing you want to start with, right? You want to start with the simplest thing, and maybe there are simpler algorithms and simpler approaches that work for you as well, and that's great, right? But there are areas where this can help you a lot more. So in terms of the compute itself, we've done a lot of work to really push the state of the art. The TPU v3, and this is a tensor processing unit. It's really focused on, it's a custom accelerator that's focused on really optimized for deep learning. And we built that. As you can see, it's a 420 teraflop machine in a single board. And with lots of memory, we use that a lot internally, of course. And we've put a lot of these together to provide effectively what's a really, really large supercomputer. In fact, at 100 petaflops, it's, I believe, among the top 10 supercomputers in the world. So we've built this huge processing power to be able to really push the state of the art, push our products, make things much, much better. And we make that available externally as well. So for folks who use Google Cloud can access this kind of compute to do the things you want. So, one was the compute itself. The other part is data. And for data, there are lots of data sets available now which you can do things. There are probably very business-specific data sets that you have in your company itself that hopefully you can leverage and hopefully you're working to make available as well. But there are lots of, for certain kinds of things, for image, speech, text, there are lots of external data sets, and we've done our part to make more available. This one is called Open Images. Google made that available. I believe it has a few 100 million images in there. And it has lots of details in terms of labeling, object detection, and so on. So you can use that to solve different kinds of problems. Turns out if you train a model on, say, vision, speech, text, the kind of things that are common across your data set and an external data set, you can often train on a very large data set first. And then even if you have a tiny data set, you can use that to improve and focus on what you're trying to do. And then finally, TensorFlow, the tools really, the systems part to make sense of this, to leverage the accelerators, to leverage the algorithms, and to make a lot of these algorithms available. And this is something I've been working on, and it's open source, it's available to everyone, lots of people in the world are using it. In fact, these dots sort of represent the people who've shown interest in TensorFlow. We know people across the world are using it in pretty much every single time zone in the world. And in fact, going all the way in the Arctic Circle down to the Antarctic Circle. So pretty exciting to see that being used across the board. And we've had over 41 million downloads so far for that. So lots of developers trying out things and doing some really exciting things with it. So let's take a brief look at a few things people have done with these tools, even outside what we're doing. In this case, an ML researcher got together with an astrophysicist took a lot of data that was there about potential planets out there and signals which people try to use to find planets. Before this, people would spend tons and tons of time using different kinds of statistical methods as well, but really spending tons of time to find planets. And in this case, they were able to find 2 new planets. In fact, since then, they've found many more as well in the Kepler system, which is, in fact, very much like our solar system as well. Another example is this. There's this company called Connectera, and these are it's based in Netherlands. They basically have this device which is sort of like a Fitbit for cows. It tracks how the cows are doing, tracking all of that because their customers are all these farmers who want to make sure that their cows are healthy, etc. And finally, the environment itself. There's a lot of stuff happening in the environment. People want to fight climate change, and one of the things in this case these engineers did was they created these little devices that would listen to the sounds and stuff and try and identify if somebody was trying to do illegal logging and make sure we are preventing deforestation and so on. And they're using these tiny devices that can be put on these trees and so on to track these things. So of course, with this technology, we want to make it easier and accessible to more people. So we have these building blocks that we've made available in cloud. These are a lot of these things for different kinds of data sets. We didn't talk so much about structured data, but we have a number of things in there for recommendations and so on as well. And we want to really package that technology and the research that goes into improving this over time. The last thing I wanted to mention there, though, was the last thing that we've needed is the ML expertise. It's still to really push the state of the art, it's still very, very hard, even with the best tools often. And these 3, if you're familiar with them, they are the Turing Award winners for this year, and they got an award for pushing the state of the art in deep learning. They are really the one in the middle. Jeff Hinton is known as the godfather of deep learning, and the other 2 are, have really done a lot as well in the space. So of course, there are only 3 of them. In fact, even talking about ML researchers and so on, there may be thousands in the world at most, right? Yes, we talked about training data scientists and stuff, and we should totally do that, and that's something we'll continue with. But that's, it's going to take its time and improve things. So there's something we are doing to help, and one of those is to really think about, can we automate more of that process of, okay, once you've defined the problem, can we help you solve that problem, to automate that entire process? And in this case, if you have some structured data and you know exactly the problem, if you can say what's the problem that you're trying to solve, then AutoML tables really tries to pick out the best algorithms that you need to solve that particular problem. In fact, we have this open community on this place called Kaggle, where lots of data scientists compete for different kind of competitions and just share different ideas as well. And there's this offline Kaggle days where you have a competition around some specific task, where a bunch of data scientists get together and really try to solve a specific problem, just compete to solve that problem. And so earlier this year, we had this AutoML tables compete with the data scientists as well. And it turned out it did pretty well. So it got the second spot in that competition, where it, in fact, combined with the best one, they improved on the overall score as well. So it's really good for lots of different problems. Again, like with any tool, it's not a panacea for solving every single thing, but combined with the process and stuff. And again, there are lots of cases. If you have great data scientists, awesome, right? You should leverage them. But there are lots of places where we don't have data scientists and we need more. And that's the kind of thing, that's the kind of place where this can really change the game. And so, there are lots of different things that we're doing with AI, lots of different things that we're doing to push the state of the art, to really combine AI with different things. And I would love to, leave you with just this final thought. Thank you.